It's another tech day. For everyone who was watching this series for a longer period of time, you might be surprised that I changed my wallpaper from the old Windows 95 to this basic one. What I decided actually is to change my wallpaper in every episode from now on. I have a lot of them, so I want to use them. Also, in today's episode, I won't be playing any games. We are going straight into the work. And as a refresher, as a reminder what we did last time, we are basically following the book Structure and the Interpretation of Computer Programs. And we were working on some pretty interesting problems in regards to the Newton's method of finding square roots and the implementation of this method in Lisp. Without further ado, let's continue. Now, we did all of this in the last episode. If I remember correctly, I spent almost 1 hour trying to work on the exercises. The point of this was that the square roots are just an excuse, because, and it says in the book's not teaching us how to compute the square root. It's teaching us how to think about programs and how to think about solving programs, and more specifically, how to structure a program so that it mirrors the structure of the problem itself. And one of the core ideas is decomposition, or decomposition into meaningful subproblems. So the square root program that we did the last episode naturally breaks into questions like, how do I know when we found the square root, when we are done? And for that we can use the good enough method that we created here. How do we improve, I guess? And for that we also created a method, namely improve. How do we repeat the process? And for that we created a procedure called square root iterator. And how do we start? There's a method called square root. And it's not arbitrary. We didn't split our program into first 10 lines and the next 10 lines. We basically split the program so that each procedure solves one identifiable task. And why this is important is that we don't want simply to divide the program into parts. We want to have each procedure be a reusable independent unit of thought. And when we use, where is it? Good enough. Here. So when we use good enough procedure, and we rely on the square procedure, and this was really hard for me to think about initially, we do not care how square is implemented. We only care that it returns the square right here. And that's the only thing that matters here. So we need to think in terms of what a procedure does, not how it does it. And we also need to think about certain procedures as black boxes, and we need to have this black box thinking, sort of. Because from the perspective of, again, let's go back to the good enough method. From the perspective of good enough, square could be written with a multiplicator here, or with any other combination of symbols, or even with some hardware instructions. As long as it just inputs the guess and returns to us the square of that number, it's okay, and it's interchangeable. So when we define procedures, we should be able to suppress details, because the user of the procedure may not have written the procedure themselves, but may have obtained it from another programmer as a black box. A user should not need to know how the procedure is implemented in order to use it. So it's decomposition and black box thinking, which was, at least for me, a really complex topic to not understand, but implement, because I always was interested how this works. How does a layer below it works and behaves, and it just takes more time than it's needed, especially when we need to deliver on time. Again, there is a subsection on how to think, and instead of learning syntax, we should learn what makes our programs reliable and understandable. Let's say, again, we have a square method here. If I had the exact same procedure, and only instead of x, I had, maybe let's use a different color, I had a y here. If I changed x to y, and if this also changed the meaning of the program, then programming would be hopeless. The meaning of the procedure must be independent of the names of its parameters, which does sound obvious. Also, the x that we have here and the x that we have here, so these two x's, because good enough is calling square here, they are two different x's, and they must not be the same variable, because if they were, calling square could overwrite x in good enough here. And behavior of good enough would depend on how square is written, and square would not be a black box anymore. Basically, this means that this is a concept from a general concept that you learn when you've been taught programming. Local variables are protecting procedures from each other, and local variables have their own scope. And also, we have something called bound variables. Again, going back to the square method right here, a variable is bound if its meaning is given locally by a definition. X right here is a bound variable because it scopes the body of square, and it only exists in the body of square. It lives in the body of square. And renaming it to y changes nothing. And if we call this method at a certain point, by using square x or square y, it changes nothing, and this is equivalent as definitions go. And a free variable is if a variable that's not defined locally. So good enough, there are two bound variables, yes, and x. And all the free variables are the square right here, the absolute, the greater than symbol, the minus symbol, because their meanings come from outside of these definitions. If you change one of these, the meaning of good enough change. And then scope, which is another concept from programming. Basically, the scope of a variable is the region of the programming where it has meaning. Like here, the scope of x is the body of the procedure's square, because outside of the body, it doesn't exist. Which is actually good, because it guarantees no accidental interference, the behavior is quite predictable, and modularity and reusableness, is a word, I don't know, is enabled. Now, why is this important? Because procedures behave like mathematical functions. If you get the same inputs, you're going to get the same outputs. Internally, the names don't matter, and implementation details don't leak. If we didn't have local names and binding rules, procedures would not be interchangeable, abstraction would collapse, and black boxes would be lies. If there was a one-sentence takeaway, means that good programs depends on what variables mean, not what they are named. All right, so this is basically just introductory stuff. And there is another concept that the book is mentioning. It says, basically, in short, programs should expose what users need and hide everything else. And this is about encapsulation. The original problem that we had here above, we defined four different methods, four different procedures, all at the top level. We have square root, iterative, improve, average, good enough. This is bad because users only care about square root. And the helper procedures are polluting the global namespace. And also names like good enough are extremely generic. In large systems, name collisions also become inevitable, which does not scale in a big project. Does not scale. So what we could do is, and one solution is to have fine square root, and then here I could also define all the other methods like good enough, define, improve, define, square root, iterative, and so on and so on. If we write our implementation of procedures like this, all of the internal procedures are private. They exist only inside square root, only inside squirt. Other code can define their own good enough without conflict, and the user sees only one clear interface, which is square root. And this is called the block structure. Now, we could even refactor this further. Instead of passing the x around, we could just get rid of it because it's already bound right here in square root. And internal procedures are inside the scope of x. Passing x, again, is redundant. In our case, we can just use it from the square root definition, and now it's free from the internal procedures, but it's still bound by the enclosing square root method. This is safe and this is intentional. And because we have scoping, the x inside good enough that I have written because I don't have time. The x inside good enough refers to the x in square root, and same thing for the x in square root iterative. It's not some global x, it's not a Color's x. It is called lexical scoping. Because it depends on where the code is written. If we have written our code here, this x is visible anywhere in our program, basically. And this is not only powerful because we can safely share our context, but because we don't have any accidental interference, we have predictable behavior and the ability to simplify interfaces. All right, this is basically all relatively simple. I want to see something else. Let me change some colors around. Now, it says here, the ability to visualize the consequences of the actions under consideration is crucial to becoming an expert programmer, just as it is in any synthetic creative activity. Because we need, and we have to reason backwards, we have to know how to plan, we have to know how to develop, and we need to know the course of action to be taken by a process and how we control it by the means of program and where the execution goes. Basically, we need to mentally visualize the processes generated by various types of procedures. Only after we have developed such a skill can we learn to reliably construct programs that exhibit the desired behavior. What do we have here? Linear recursion and iteration. And it's written here, we begin by considering the factorial function, which is defined this, and factorial, it's n times n minus 1 times n minus 2 times 3 dots times 3 times 2 times 1. And it says here, there are many ways to compute factorials. One way is to make use of the preservation that n factorial is equal to n times n minus 1 for any positive integer n. So n factorial is equal to n times n minus 1 factorial for any positive integer. And we can compute n factorial by computing n minus 1 factorial and then multiplying the result by n. If we add the stipulation that 1 factorial is equal to 1, this observation translates directly into a procedure. So how does this procedure look like? All right, so this is the procedure. And how we can compute it on a simple example, let's say. It can be on a factorial of 4, let's say. And then I have 4 here, not equal to 1, and then I say, okay, 4 times factorial of n minus 1. So it's gonna be multiplied by 4 factorial of 3 multiplied by 3 factorial of 2 multiplied by 2 factorial of 1 . And then I have here multiplication. I have 4, 3, 2, 1. And now I'm going back. 2 times 1 is 2. It's going to be 4, 3, 2, 4, 6. At the end, it's 20, 24. Okay. So the book says there's another way of computing factorials. Okay, now it's comparing the two processes. I'm not interested in this. Let's see. Now, let's do an exercise from the book. It says each of the two following two procedures defines a method for adding two positive integers in terms of the procedures inc, which increments its argument by 1, and dec, which decrements its argument by 1. Using the substitution model, illustrate the process generated by each procedure in evaluating plus 4, 5. Are these processes iterative or recursive? So these are the two procedures, and both of them define a method for adding two positive integers in terms of the procedure's inc, and it increments its argument by 1. All right, so the question is, illustrate the process generated by each procedure in evaluating plus 4, 5. Are these processes iterative or recursive? Where are we? Okay. What do we want to do? We want to learn to see what the procedure does over time using the substitution model and to distinguish between recursive processes and iterative processes. So these two are right here. They're both correct mathematically, but they both produce very different processes. We will evaluate 4 plus 5 or plus 4, 5. This is the first definition here. All right, so what are we substituting here? Instead of plus AB, we are going to have plus 4, 5. A is not equal to 0. So we will have from here, we will have inc plus 3, 5. And we can substitute again. And I think you know where this is basically going. We're gonna have inc plus 2, 5. And if we substitute again, we're gonna have 3 increments all the way to the base case. And the base case says inc 1, 2, 4, 0, 5. And now, because this is the base case, we have 5 here. And then we unwind. This is going to be 6, 7, 8, and 9. This computation builds up deferred operations. These must be remembered until the base case is reached. And this is a recursive process because there's a chain of pending operations. The interpreter must remember each inc, and the memory grows with A. And the second definition, same thing. Let's substitute plus 4, 5. So what happens here? Plus 4 and 5. Sec A increase B. All right. So we are calling these methods immediately. So now we're gonna have plus 3, 6. We're gonna have plus 2, 7. And it's gonna keep on going until we hit plus 0, 9, and then we return, because the base case says if A is equal to 0, then we return B. And there's no deferred work. At each step, A decreases, B increases, and the state is fully captured by AB. And this is an iterative process because there are no pending operations, there is constant memory usage, and the state is carried forward explicitly. All right. Let's move on. Okay, let's do another example. It says, the following procedure computes a mathematical function called the Ackermann's function. There is this function here. I'm gonna I'm gonna paste it. And I'm gonna add it here in a moment. But it says the following procedure computes a mathematical function called Ackermann's function. What are the values of the following expressions? Consider the following procedures where A is the procedure defined above. Give concise mathematical definitions for the function computed by the procedures f, g, and h for positive integer values of n. For example, kn computes 5n squared. All right, I'm gonna have all of these ready. Actually, wait. Why am I being an idiot? All right. Here I have this exercise. The following procedure computes a mathematical function called Ackermann's function. All right. So let's first understand what this function actually does and what it is. Ackermann's function. So the definition of it is a x y, and then if y is equal to 0, we return 0. If x is equal to 0, we return 2y. Wait, so y is 0. It's 0. X is 0. We get 2y. And if y is 1, what do we get? 2. So this is a condition. And there's also the recursive case, which says a xy is equal to what? Equal to a x minus 1. And inside I have a of x y minus 1. I have no idea what it does, but let's compute for here. It says what are the value of the following expressions. So we are gonna compute this for the first case of a being 1 and so how is this working? I mean, we can simplify this first. We can simplify it by trying to solve a 1 1 a1 1, and what's happening here, because y is bigger than 1, I'm returning 2 by default, and then this method would be a zero a oh sorry, not 0, it's supposed to be 1 y minus 1. Sorry, a1 1 is the basic rule, basically saying here, if y is 1, we are gonna return 2. So this is 2 by default as the return value, and here we are solving the more complex value where y is bigger than 1. So what's this? What do we else have? If x is 0 here, as this, what do I have here? Because we have 0, we're going to return 2 times y, but y in this case is this value, so I'm gonna interchange it. So it's gonna be 2 times a 1 y 1. So what's happening here? It says that it's doubling repeatedly. A of the case 1y is But my question is, I want to understand, why is this multiplying? Why is this doubling repeatedly? Why? Why? Why is this doubling repeatedly? All right. We want to understand why this turns into repeated doubling. Here it says, we need to specialize the definition to x equals 1. And if we put here only a 1 and y is still the unknown, we can plug in all of these values and we can say, all right, it's a 1 minus 1 is 0. And here we have another a of 1, y minus 1. All right. Now we have a rule that says if x is equal to 0, we return to y. So I can substitute and say a0 y is basically to y, right? And if I replace this here, it's gonna be 2 times a1, comma 1 minus 1. So if our base case for a11 is 2 and we have a recursive rule here, what's happening here? Ah, right, so it's doubling, it's repeatedly doubling. For y equals 2, we could have a1, 2, it's gonna be 2 times a1, 1, it's gonna be 2 times 2 is gonna be 4. For y equals 3, it's gonna be a1, 3, it's gonna be 2 times a1, 2, 2 times 4 is gonna be 8. All right, so it's multiplying. Each step multiplies the previous result by 2. So if I have this value of, again, a1, 10, and if we are generalizing here, and saying, oh, that a1y is basically 2 squared y, this will be 210, and it's gonna be 104. Let's analyze another example here. 2, 4. A 2. Let's see if I can solve this on my own. What is the base case here? If a let's create one case. If we have a to 1, we are going to the case where we have a 2 minus 1 is going to be 1, comma a going to be 2, and y is going to be 0. So if we substitute the 1 to the 1 where? No, not yet. We are not substituting yet. We are substituting here. If y is equal to 0, we do return 0 here. So this one is going to be 0. But this one is going to go to 0, and then we are going to return 2 times y. Right? Am I understanding this correctly? Am I an idiot? Most probably. We have x minus 1. And if this is going to be 1, it's going to be 2, and this is 0. So you're going to have a of 1 slash a of 2 is 0, because y is 0. This is going to be, you're going to have a 1 0. How is this 2? How is the base case of 2 comma 1 2? I have no idea. I have no clue. I'm an idiot. I don't believe. Okay, this all is kaput. It should be like this. Basically, I just got a 2 comma 1, and because y is 1, we are just returning 2. Wow. Wait. Let me just do something else. All right, boys and girls, let's take a quick break, and I'm gonna be back. Definitely. Let me just close this. Can I close this? All right, I can. We are gonna be back.